Hi learners, welcome back. It's week 12. And along with last week on unsupervised learning, this week we'll be examining one of the frontiers of machine learning research, which is really exciting, namely that of reinforcement learning. Now, reinforcement learning is a very interesting and simple concept all at once because it mirrors much of the decision processes that we have to actually face as humans every day. Idea that there are sequential episodes and there's nobody really telling us what to do or how to do it. There might be some type of guidance helping us to decide whether we're fulfilling our rewards, for example, eating food to feel sated, or doing well on exams, but there's no specific supervision signal. The key characteristic is it is this time sequential and has particular decisions to be made, hopefully in the optimal manner. So we're going to get started on this right now, but just to note that there are many, many different ways of executing reinforcement learning, and what we're doing today is just scratching the surface. Let's take a look, shall we? So let's do what we typically do and recap what we learned last week in unsupervised learning, and then proceed to forecast what we're going to learn today. In last week's lesson, we talked about dimensionality reduction as a key application of unsupervised learning. The idea here is to find some type of meaningful low-rank approximation of the original data. We saw two different methods for doing that, including using PCA and one particular way of doing PCA using SVD, right, singular value decomposition. The whole point of this is to try to find orthonormal basis that helps to determine and characterize most of the signal by finding those bases to have the most variance in our data to determine the principal components. In the second half of the lecture, mostly in the post-lecture, we examined clustering. In clustering, we assume that we're going to iteratively learn without labels by assuming that the guesses for our clusters are correct, and then reassigning the data to clusters, and then iterating on the other side, right? So to be able to assign the data to the model through an expectation step, as illustrated by this arc, and then estimating the likelihood of the model and trying to recreate the model to maximize the likelihood of the data. That was our M step. This week, we're going to be looking at reinforcement learning. And reinforcement learning has its own set of basic anatomy and terminology, which is very important to understand. So there's the ideas of a policy, meaning an action map about what to do when faced in a certain situation, the reward, about what type of utility we get from being in a certain state, and the observations and the environment for both the agent and the environment. We're going to also examine a very critical property that allows calculation to proceed with ease, which is the idea that we encode everything that we need to know about the environment in a single state. And this is facilitated by the Markovian property or Markov property. And it lets us define the idea of a Markov decision process. Finally, we're going to go over a very key concept in reinforcement learning in terms of the Bellman equations. Okay, the Bellman equation is just some type of recursive form of calculating future rewards and valuing them at the present time step. With that, we can get started.